Hello everyone, my name is José Pombal and I'll be presenting fairness-aware data valuation for supervised learning. The main motivation for this work is that training data quality is known to be crucial for both the performance and fairness of supervised learning models. However, the field that studies how to measure this importance, data valuation, has only concerned itself with measuring the value of training points towards a single metric of interest. Be that a performance metric or a fairness metric, no work has ever joined the two objectives, which is the goal of fair machine learning, to build systems that are both performant and fair. So we introduce a framework, fairness-aware data valuation, that allows us to incorporate those two objectives into data valuation. We introduce an entropy-based metric that joins the two objectives and allows us to compute instance importance in a much faster way than existing methods. And finally, we show that we are able to pre-process training data with our framework in such a way that models trained on that data exhibit very promising fairness accuracy trade-offs in a real-world fraud detection application. Our framework can also be applied to other applications like exploratory data analysis, active learning, and data generation, which is a priority for future work. So what is our framework about? If we take a step back and look at data valuation in its more normal sense, the goal is to find the training instances that contribute the most to performance on a given predictive task. So we can call this value of each training instance I, V, Y, I. And here, Y serves to denote the fact that the value is being computed towards some performance metrics, such as accuracy. In our case, it's recall. It could be any performance metric. And what we do in our framework, fairness-aware data valuation, is extend this notion of value to a broader notion of utility, which joins two terms of value. One value of performance, VYI, and a value towards fairness. So this VZI here denotes the value of instance I towards fairness with respect to protected group Z in the context of some predictive task where our target is Y. So we're always in this context of some downstream predictive task, which in our case, it's fraud detection. The alpha term governs the weight that we might place in performance and fairness, which might vary between applications, but this is also task dependent, of course, and the specific formulations of V and the utility function itself are also task dependent. One advantage of our framework is also that it can be extended to other notions of fairness, so not just with respect to one protected attribute like race or age or gender, but with respect to many protected attributes. We might want to ensure, for example, that our classifier has equal error rates in age groups, races, genders, etc. And we can, to that end, if we want to consider that, we can just add those terms to the utility function. And from here on in, I'll be referring to Y as the target of our classification task. So in this case, fraud, it's a binary value, but it could be continuous or categorical. And Z will be the protected attribute. In this case, it's always binary as well, but the framework allows it to be continuous and categorical. So how do we go and calculate those V's in the utility function? There are existing ways to do it in the literature, but they are quite slow and they are not necessarily easily extensible to fairness. So we take an entropy-based approach. And why? If we look at active learning, we see that entropy has already implicitly been used as a data valuation metric, in the sense that when we are doing active learning, we choose to label the points, first that where our classifier has high entropy. And why? Because we believe that the classifier will learn more from training on those data points than from training on points where it is very sure about the label. This is just a heuristic because being sure doesn't necessarily equate to being right, but it has been shown to work well in a series of tasks. And Okay, so this gives us our metric for data value with respect to performance, but what about fairness? It turns out that we can also use entropy. But instead of using the entropy of a classifier trained to predict y, which is our performance valuation, we will use an entropy of a classifier trained to predict z, our protected attribute, using the same features that we might use to predict y, so that's a feature group x, and also y. And why does this work exactly? Imagine a very simple scenario where we have a variable z, for example, age group, with two groups, 0 and 1, and both of them encompass 50% of the data set. If we train a classifier to predict this group with the rest of the features and the target in our data, and the classifier had a random performance, that could equate to the classifier always predicting, for example, 0.5 for every instance. And that would mean essentially that the classifier has no way of establishing a relationship between z, x, and y, which also implies that when that classifier is used to predict y, which is our final downstream task, it won't be able to leverage z to obtain better performance. So in essence, that would mean that we would not need to be worried about different groups having different error rates, etc., because the variable simply wouldn't be discarded. So I give you this sort of extreme example so that you understand that entropy in general can be used as a measure for how much a certain data point contributes towards unfairness or fairness in the final task at hand. And in particular, we will prefer points, so the points that will have highest utility in our framework are points that have high entropy on y, but also high entropy on z, because of the reason that I explained before, that it will be hard to draw a connection, using those points to draw a connection between z, x, and y. And so we can take this framework and apply it in an unfairness mitigation application. And we follow the following steps. We take our real-world bank account fraud dataset. There are more details about it on the paper. And we first calculate entropy-based utilities for all training instances. We do so by creating a model to predict z and a model to predict y. We train them on the training set and obtain entropies for the instances in the training set. And we combine them in, for example, a weighted average to obtain our utilities. And these will be our valuations to use afterwards. Then we sample or reweigh training instances before actually training our final fraud model in one of two ways. Utility-aware prevalence sampling, where we balance fraud rates by discarding the negative examples of the advantaged group, or utility-aware reweighing, where we assign higher weights to instances that have higher utilities in the hope that this will lead the model to be more performant and fair. We then calculate performance and fairness on a holdout test set, and we compare it with two alternatives from the literature that can be sort of seen as random baselines for our two approaches. And our final results are as follows. We have performance on the x-axis and the fairness metric on the y-axis. In the paper, we also show other fairness metrics, and the conclusions are similar, that our models, which are colored from green to red, exhibit consistently the better fairness accuracy trade-offs. And here the green to red is, the greener a model is, a point here in the plot, then the more weight was placed in the utility function towards fairness, so the fairer models should be, and the redder it is, the more weight to performance. And as you can see, there is a trend of the greener points tend to be a bit less performant but more fair, and the redder are less fair and more performant. And this is, our models exhibit the better trade-offs compared to the baselines. So to wrap up, we introduced the fairness-aware data valuation framework and the metric as well, and we showed how it can be used to lead to better performance, to better fairness at a low cost in performance. And for future work, we'd like to extend this unfairness mitigation benchmark to more data sets, tasks, and models. and also evaluate our framework in other settings like active learning. Thank you very much for your attention, and feel free to check out the paper in this QR code.